Hello everyone. Today we're going to be doing an introduction video on error bounds for Taylor series. I'm going to start off by talking about alternating series bound, which is the first half of the error bounds. And you do this in order to approximate for an alternating series, you have to look at the next term. So for example, like if you have like a series till k, you have to approximate using the k plus 1 term, and this is greater than equal to, the absolute value of this is greater than equal to the entire error of the actual value. And this is a quick way to know how accurate your partial sum is, right? And like, for example, if the fifth term is 0.01, then using the first four terms means that the error is less than equal to 0.01. And for alternating series, we would actually take the absolute value. And this applies to alternating series where terms are decreasing and approach zero, right? Because they're converging. A quick example. Okay, so this question says use the first four terms of the series to approximate the sum, right? And we can see that it starts at n equals 1. That means that theoretically we have to add up the AF1 plus AF2 plus AF3 plus AF4, and it's saying calculate the error that this will have compared to the alternating series bound. So that means that the absolute value of the error based on the formula on the last slide is less than equal to the fifth term, right? So that means we just have to plug in n equals 5, and then we get the absolute value of error equals minus 1 to the 5 plus 1 over 6 over 5, sorry, equals 1 over 5. That means that the error is less than equal to 1 over 5. And I got rid of the absolute value since this is a positive number. Here's another example. This is a little bit more complicated, and it says that let the sum 4 be the sum of the first four terms. That means that means AF1 plus AF2 plus AF3 plus AF4. So then this is saying which is the best upper bound for the error. So this basically is saying that it's basically doing the same thing, calculating the error. And we know it's an alternating series because there's minus 1 over here, right? So because S4 is the sum of the first four terms, we have to look at the fifth term, right? So that means the absolute value of the error is less than equal to AF5. And now we have to calculate AF5, right? And AF5 is just, you have to plug in n equals 5. So it's minus 1 to the 5 plus 1 over 5 squared, which is 1 over 25. That means that the upper bound of the error, which means the max value the error can attain, is less than 1 over 25.
Alright, so I will be talking to you about LeBron error bounds. So this is going to be basically when used when the series is not alternating. So like alternating series is like when it goes from like positive to negative, you can usually tell that if it's like a -1 to the power of n plus 1 in it. But this is used if it's not alternating. So basically it will give you the upper bound of an error. So when you approximate f of x using a Taylor polynomial, and the formula is basically this. Basically what this is going to be your error. So and it's going to be less than m, which is going to be the maximum value of that function in the domain from like a to x. You'll see this later when we do the example problem. And then x minus a is going to be like your bounds, and then that's the power of n plus 1 all over the n plus 1 factorial. And n is going to be the degree of the polynomial, and then a is going to be the set of the Taylor series. So that's going to be your general formula. It's probably the only one you're going to have to like memorize for error bounds, and it ensures that your approximation is within a known range of the true value of f of x. So now we'll get to an example problem demonstrating this concept. So we have that f of x goes e to the power of x, and p of 2 of x with the second degree Taylor polynomial such that x goes 0. So what is the maximum possible error when using p of 2 of 1 to approximate f of 1? So use the formula again, which is going to be m over n plus 1 factorial times x minus a to the power of n plus 1. So we know that n is going to be the 2 because it's the second degree polynomial, and then x and a are going to be well, a is the center of it, so x is going to be 0 and a is going to be 1. Yeah, so, and then we know that the maximum value for e of x, so because it's in that domain of, so if you look at the graph here, it's going to be that domain of 0 to 1, so e of x is going to be like this, right? So the maximum value in that domain is going to be at x goes 1, so basically the maximum value would just be e. So that means you would have, in this formula, you would get e over 3 factorial times, because this is absolute value, remember, e times 1 to the power of 3. And 3 factorial is going to be 6, so you would get e to the power of 6, which is going to be c. So now going to the next example, which is going to be actually the 2025 AP Calculus BC on FRQ exam. So this is basically just saying the second degree Taylor polynomial for about x equals 1 is approximately 1.1. So given that the f to the third degree is going to be less than or equal to 60 in interval 1 to 1.1, show that it differs at most 0.01. So let's just apply the same formula again. So that's going to be max over n plus 1 factorial times x minus a to the power of n plus 1. X is going to be equal to 1 and then a is equal to 1.1. Because this is absolute value, it does not matter too much what you assign to these, as long as one number is the center and the other number is where it's approximating. So we know that in this second degree, it's a second degree Taylor polynomial, so we know that it's going to be n equals 2, and then the maximum values it gives us here, right? In this interval, it's always going to be less than or equal to 60, so we know that the maximum value here is going to be 60, so m is equal to 60. And x minus a, that's just going to be 1 minus 1.1, which is going to be 0.1 when you take the absolute value of that. So that'd be 0.1, so that means you would get 60 over 3 factorial times 0.1 to the power of 3. And 60 over 3 factorials, that's just equal to 10 times 1 over 10 to the power of 3, which is going to be 1 over 1,000. And then when you do that, you get 1 over 100, which is equal to 0.01. So that's how you show that the error is going to be less than or equal to 0.01. So that is how you use the Lebrun error in this scenario. All right, so that is all those are both of the error bound formulas that you have to know. So thank you for listening, and we hope this helps you on your next test.